Spanning tree protocol. So the spanning tree protocol, its whole purpose is to prevent redundant links from switches and prevent routing loops of happening. The issue here is we try to add a redundancy by connecting multiple switches with multiple paths together. But if we're not careful and we don't have spanning tree enabled, what we can end up having is a loop of our traffic going around and around, which will cause us a broadcast storm. We talked about earlier our availability being measured in the 5 nines of availability, 99.999%, which gives us only 5 minutes of downtime per year. Because of this, we've added more routers, more switches to create more redundancy. SPB is used in larger environments. It's the shortest path bridging. But for our exam, we're going to be talking about STP, Spanning Tree Protocol, because it's what's used in smaller, small office, home office, and smaller business environments, which is where most Network Plus technicians are going to be working. And again, here's another standard. We have the IEEE 802.1d, which is Spanning Tree Protocol. 802.1d for Spanning Tree Protocol. So, if we don't have Spanning Tree Protocol in use, what ends up happening? Well, if we don't have Spanning Tree Protocol, what will end up happening is we will get a MAC address corruption. Our table will get corrupted. For instance, in here we have PC1 in the upper right trying to send in information to PC2 down here on the left. When he sends that information, that ARP request is going to go and it's going to hit both of these switches because they're both on the same bus line here. When that happens, switch number 1 is going to send that out to both PC2 and switch 2. Switch 1 who receives it, or switch 2 who receives it, is also going to send it to PC2 and switch 1. And so what ends up happening is this all A address that PC1 has is going to end up getting entered in the table on both this port, this port, this port, and this port. Because as it hits that, it goes around and it starts creating this big circle. So now, how do we get to PC1? Nobody knows because you have multiple ways to getting there, and it confuses things. And so both switches are going to end up seeing traffic on the gig 01 ports and the gig 02 ports for PC1 and get very confused. And this corruption ends up occurring. So STP is going to stop this from happening. The way we do that is what we do is we create a root bridge and a non-root bridge on all of our switches. So on these switches, each switch is going to be elected to act as a reference point for the spanning tree. If it's the root bridge, it is going to be the main reference point. So in our example here, switch 1 became our root bridge. The switch with the lowest bridge ID is elected as the root bridge. And in our case, that is done, it's usually done based off their MAC address. In our case, we're just using switch 1. The BID is made up of a priority address value as well as that MAC address, and whoever has the lowest value is the one who is going to be getting it and being the root bridge. All the other switches in the topology will become the non-root bridge. So in our example here, we have our root bridge of switch 1 on the left, and we have our non-root bridge on the right. And the reason for that, as you can see, even though their priorities were equal, the MAC address for switch 1 was all A's, the MAC address for switch 2 is all B's, A is less than B. So that's why switch 1 became our root bridge. So on your switches, you're going to have root ports, designated ports, and non-designated ports. The root port, every non-root bridge has a single root port on it, which is the port that is closest to the root bridge in terms of cost, which is a whole lot of words to say every switch that isn't root needs to have a place that the root can consider the reference point for that particular switch. And so what ends up happening is if all the costs are equal, the lowest port number is going to be chosen. And when we talk about costing, we're talking about the speed of the connection going to it. So up on the top graph, you can see both of them are fast Ethernet Cat5, and they're both have a cost of 19. In the bottom one, you can see that the top network is Ethernet, which is Cat3, only 10 megabits per second, so it has a higher cost. And the fast Ethernet has a lower cost because it's a faster connection at Cat5. So in that case, our root bridge went to the lower cost one. In the top one, because both connections were equal, it went based off which one was the lower port number, port 1 versus port 2. But in the bottom one, it went based off the fastest speed, which was port 2 in this case. Designated ports. Designated ports are on every network segment. They have a single designated port, which is the closest to the root bridge in terms of cost. And if you're on the root bridge, you're automatically going to be the designated port. So as you can see here, both ports on my root bridge are designated ports, the top and the bottom. Over here I have my root port on the non-root bridge, and that leaves us with the last port over here being the non-designated port, which is the port that will block traffic to ensure that we have a loop-free topology. So what's going to end up happening is when PC A tries to send stuff to PC B, it's going to hit the root port and it's going to hit the designated port. The designated port, because it's on the root bridge, is going to pass that information out, this port down here, and it's going to go both to the PC and over here to the designated port. But when this non-designated port receives the information, it's not going to forward that traffic. It's going to block that traffic. That way we have a blockage in that loop, and we don't have that loop anymore that we had before. And I'll show you a couple of pictures that will help make it a little easier to understand. So the non-designated ports do not forward traffic during normal operation, but instead they do receive what's called the Bridge Protocol Data Units, the BPDUs. If a link in the topology does go down, the non-designated port detects that failure and then transitions into a forwarding state and starts sending traffic through again. If it doesn't transition immediately though, it does go through 4 different states. First, it starts as blocking, like we said before. If it's a non-designated port, it's not going to send out data, right? So it's going to receive that information, but it's not going to forward it, and it's just used to basically understand what the architecture is looking like. Then it starts listening, and it starts populating its MAC address table, but again, it's still not forwarding any frames yet. Then it goes into learning, where it starts processing those PDDUs, and the switch determines its role in the spanning tree. And then, if everybody else is down, he will start forwarding the information so that the network stays online as well. So we talked about cost before for the ports. The way that the costing is done is based off the link speed. So in the chart below you can see Ethernet, which is 10 megabits per second, has a cost of 100, fast Ethernet of 19, gigabit Ethernet of 4, and 10 gigabit Ethernet of 2. These standards were made a long time ago before we had the high-speed networks we have now. They're actually working on a new STP standard called long STP that will be adopted over the coming years because our links keep getting faster and faster. And what they're going to do is they're going to make the ranges go up to 2 million now instead of only going up to 100. So the Ethernet that's currently 100 is going to end up becoming 2 million. And then when you get into the terabytes per second of speed, we'll be dealing with numbers of 2 instead of saving 2 for 10 gigabit. So again, as we talked about with fiber, you can get up into 60, 70 terabyte links. You need to be able to have numbers to support that, and that's why they're redoing that standard. So a broadcast storm occurs if the STP is not working properly. And as I showed you guys before, as information comes in from PC1, if it hits both switches and is routed in a circle, they start flooding each other with data because nobody can find where PC1 really goes, and it just keeps going in a circle. This happens when 2 or more switches receive a broadcast frame. They forward that frame to each other, and then each of those will forward it out again, and each of those will forward it out again, each time multiplying the number of frames that are going out, right? So if I tell John, hey John, broadcast this, then John broadcasts out to 2 people. Those 2 people now broadcast it out to 4 people. Those 4 people broadcast it to 8 people, and we keep exponentially getting higher. And what ends up happening is it consumes all the resources in the network, and your whole network will end up shutting down. Okay. So the only way to stop it is to use STP to prevent this circular loop from happening. And that is Spanning Tree Protocol.